Okay. So let me elaborate on Poisson distribution. Poisson distribution and Poisson regression models are used to model or predict count response variables. And the count variables are often treated as though they are continuous variables. And here we can have lots of examples like number of publications, number of kids, right? Number of siblings, and the number of accidents, right? During a certain period of time, a certain location, or even in different locations, right? Number of deaths, etc. Okay, and the count response variables are a very common type of response variables, and there are a lot of applications. For example, in healthcare utilization, number of visits to clinic during a year, and quite frequently, people use linear regression models to predict or simply model count response variables. But the estimates from linear regression models quite often are inefficient, inconsistent, and biased. And later on, we will see this is related to the nonlinearity and heterogeneity innate to count regression models and count response variables. There are a variety of models based on the Poisson distribution that deal with explicitly count outcomes. The Poisson distribution can be derived from a simple stochastic process. Okay, there are a couple of assumptions. Okay, first of all, individuals are continually at risk of an event occurring, continuously at risk. Sometimes this risk, quote unquote risk, is good risk, right? Number of publications, okay? Well, sometimes can be, not that desirable, right? Number of deaths, or number of accidents, a number of flawed, let's say, products, produced from a machinery equipment in a factory. And the second assumption is that when an event occurs, this does not affect the probability of the event occurring in the future. So this is called memoryless. So there's no memory of success or failure of the same event in the past, and which is a bit of counterintuitive for kind of common human behavior, right? When something happened to us, let's say when we have the first publication, usually that's going to increase our odds of publishing in the future, right? Because we accumulate some experience in the past. That's part of the reason why Poisson distribution and Poisson regression models are frequently used as the baseline model, and the negative binomial regression model is used, predominantly in analysis of count response variables, along with, for example, zero inflated count regression models. Okay, so let me talk about Poisson distribution. Poisson distribution. What is Poisson distribution? So we say Y is a random variable indicating the number of times that an event has occurred. Okay, and we say Y has a Poisson distribution with parameter mu greater than 0. So what is mu here? Mu is a parameter denoting the expected value. Okay, using layperson terms, it's like average counts in the population. If the probability function is calculated as follows. Okay? Calculate as follows. Okay? So this is the probability for count response Y, okay, equal to a certain number. And this is the parameter mu. Given the parameter, how to calculate the probability, right? So this is what we call Euler's number, E, okay? It's equal to 2.7 something, okay? And raised to the power of negative mu, okay? A negative value of the expected count. And then multiply by mu raised to the power of y. What is y? Y is the count, divided by y factorial. Later on, I'm going to explain what is y factorial. And for y, so that is the count for the response variable, right? Count response variable from 0, 1, 2, and continue. And theoretically speaking, we could have what? The integer can go to infinity. But in practice, rarely that number goes up to, 30. I've never seen, such big number. Usually, it's under 10. And to calculate the probability, we simply, first of all, plugging, the count for y. That is, exactly, which number, which count we observe here. And also, if we know mu, that is expected count, then we can figure out that number. Okay. And mu is the expected number of events, okay, or incidents, and is equal to the variance of the random variable in Poisson distribution. And that is a very, very important assumption. It's called dispersion assumption for Poisson distribution. Okay, so the variance of that random variable is equal to the expectation of that random variable, which is equal to mu. And the only variation is due to randomness among individuals in the population. Right? So here is kind of quick explanation of that factorial, right? Of that factorial. First of all, let me explain what is a factorial for those who are initiated on this topic. So here we see we have y factorial, right? What is y factorial? Actually, we multiply integer, right, from 1 to y. So we multiply for y factorial, it is equal to what? 1 multiplied by 2, multiplied by 3, and go on until we hit multiply by y minus 2, y minus 1, until we hit 1. And here are a couple examples. So what is 5 factorial? It is the product of 5 multiplied by 4, 3, 2, 1. That's 120. And how about 20? That is already a huge number that probably we've never encountered in our real life computation. And here is a special case. So how about, 0 factorial? That is set to 1, okay? Here we can have a couple examples. For example, to compute the probability of y equal to 0, given the expected value of mu, okay? That is expected count in the population, okay? And we plug in 0 factorial here. If you remember, the formula is p what? Y given mu is equal to what? E raised to the power of negative mu, right? Mu raised to the power of y and y factorial. And since the count is 0 here, we just plug in 0 for y. And we just plug in 0 for y. And all other places stay the same. We don't touch mu. So it is equal to what? E raised to the power of negative mu. Okay, and same thing we can do for y equal to 1, y equal to 3, y equal to 20. Well, y equal to 20, that's going to be a very small probability, very small probability. And here are a couple kind of results for the Poisson distribution related to, let's say, mu. As mu increases, as demonstrated in our last slide, right? in our last slide. Now here you can find out that as mu increases, okay, the mass distribution shifts to the right. Okay, so that's property number one. Property number two, the variance equal the mean. And I already talked about this, right? It's called equidispersion. Equidispersion. That is a key assumption of the Poisson distribution. When the variance of y greater than the expectation of y, it's known as overdispersion. And it is very common in real data. And the negative binomial regression model and zero inflated count regression models were introduced to address such issue. In most cases, over dispersion is related to excessive zeros. Right? That it was simply observed, a lot of zero counts. As mu increases, the probability of zero decreases. Okay, the probability of zero decreases, as illustrated in our last slide, and will be shown in some graphs that I'll show you. And here's an example, right? So, so here they're all for zero counts, right? And as we increase the value of mu here, okay, plug in a number that I, plugging these numbers to the formula that I showed you in our last slide, right? If you remember, is the probability, for a certain count, right? Y given X is equal to what? E raised to the power of negative mu, mu raised to the power of Y, and then Y factorial, okay? So Y here, they're all equal to zero. So this is zero, this is zero. And then, okay, what we're gonna do is we're gonna try different mu. Okay, once we figure out the mu here, basically we can calculate the probability, right? Since we know E. E is a constant, an irrational number, or Euler's number, right? So if we increase mu here, that it expected count, we can see the probability goes down. Okay, so mu is equal to 0.8, then the probability of zero count is 0.45. The next one is 0.22, the next one is 0.05, then it's 0.00002. And the same thing for other counts. That is, if we hold the count constant, observed counts constant, and if we change the parameter mu, increase it, then the probability goes down. And as mu increases, actually, the Poisson distribution approximates a normal distribution. So that's the beauty of normal distribution. And a lot of times, many other probability distributions collapse to normal when the sample size increases. Okay? So here is another example, right? We have four panels of graph. In panel A, we have mu equal to 0.8. Panel B, we have mu equal to 1.5. Same thing for, not same thing, but different mu for panel C, different mu for panel D, right? As mu increases, again, we're going to use the same formula that I just talked about, right? That is the probability of Y given mu is equal to what? E raised to the power of negative mu, mu raised to the power of Y divided by Y factorial. Once we carry through the computation here, we will see that as we increase the value of mu, the Poisson distribution approximates normal. But note that here, Poisson distribution is a probability distribution for discrete random variables. So here we have a probability bars, and there's interval in between. Let's say here 0 to 1, 1 to 2, 2 to 3, because this is not a continuous random variable.